Welcome to chapter 31, where we look at some of the properties of radioactivity and nuclear physics. We'll be dividing this chapter up into several videos due to its length. So let's start out talking about the nucleus. You have the nucleus and it contains the nucleons, which is a name for the collective grouping of the protons and neutrons. The mass of the proton in kilograms is provided. The charge on the proton is given. The mass of the neutron in kilograms. And then we think the net charge on the neutron is 0. It actually has a substructure, and we'll talk about that in a later chapter. You don't need to memorize these numbers. You'll have a table you can look up the masses when the time comes. Nuclides are the different types of nuclei. You maybe have thought of them as isotopes. That's certainly an appropriate name. But in nuclear physics, we discuss them as being nuclides. So hydrogen 1, and that's because we're talking about the nucleus itself. An isotope, you have the nucleus and the electrons to discuss. So there's a fine difference between nuclides and isotopes. And that's in nuclides, we only care about the nucleus. So you have hydrogen 1, the hydrogen 1 nucleus, the hydrogen 2 nucleus, the hydrogen 3 nucleus. These are all nuclides. The atomic number is symbolized by the letter capital Z, and it's just the number of protons in the nucleus. The atomic mass number is symbolized by the letter A. It's the number of nucleons in the nucleus, so that's the number of protons and neutrons, and the neutron number is just the number of neutrons in our nucleus. A chart of the nuclides looks a little different. We're all familiar with the periodic chart, but the chart of the nuclide is very different indeed. So we're going to come down and look at it. If you want to think of it, it's like having every single isotope, but again, we're talking about the nucleus of each one of them. We don't really care about the electrons. And this is just a tiny, tiny part of it. So you can see that we have, for example, down here, we have carbon 9, carbon 10, carbon 11, carbon 12, carbon 13, carbon 14, carbon 15, 16, 17, 18, 19, 20, 21, and 22. We have the 3 hydrogen, hydrogen 1, hydrogen 2, hydrogen 3. We have 4 helium nuclides. We have 6 lithium nuclides, and so on. So a chart of the nuclides is an enormous chart. Usually they're in book form, and these days, because everything's on the internet, it's in a digital format, and we would look it up if we were that interested in things. You're not going to have to refer to it. We will use a table to give us all the information we need. I just wanted you to know what at least a little part of it looks like. So to symbolize a specific nuclide, we use its chemical symbol, so C for carbon or H for hydrogen, its atomic mass number, and its atomic number. And our format is fairly scripted. We don't have a lot of leeway in that. So it can be in this format where you have the symbol and a superscript is the atomic mass number and a subscript is the atomic number. Or oftentimes we'll leave off the atomic number because if you have the symbol, you probably know what the atomic number is. Or if you don't want to have superscripts, you can have the symbol and the atomic mass number. And so to give you something that's maybe a little more understandable, carbon 14 could be written like this, where we have 14 as the superscript and 6 because it's element 6 on the periodic chart. Or carbon 14 could be written like this, or we can write it all on a single line. And one format is really no better than the other. It just depends on your personal preference. So we've already mentioned isotopes. Those are nuclei that have the same number of protons but different number of neutrons. So carbon-12 and carbon-14 are isotopes of carbon. Not all isotopes occur in the same percentages. You should be familiar with that. An element that is above uranium. So uranium is element 92 on the periodic chart. Anything above uranium, so trans uranium, does not occur naturally. It's unstable enough that if it once existed, it's all changed into something else. But we can artificially produce them with a little bit of nuclear physics magic. There are two elements below uranium, technetium and promethium, that are also so unstable that none occur naturally on Earth, and they have to be produced in the lab if you want to use them. So Ernest Rutherford is famous for his scattering experiment to calculate the approximate size of the nucleus. He had a radioactive source, and he produced a film of gold foil. Gold is really useful for that because it can be made extremely thin and yet still hold together. You can pound gold with a hammer to make it thinner and thinner, but that's not typically how we make our gold foil. Typically, the gold is melted, it turns into a vapor, and the vapor goes up and collects on a glass slide that's been coated with either a soap or a salt. And then you can slide it into water, and the soap and salt move away, and the gold foil floats in the water, and then you can scoop that up with a little ring, and you have your gold foil. So the radioactive source hit the gold foil, and you might assume it would just travel through because the gold is so thin, or you might assume it would hit and just bounce off. In reality, what happened is that some did just go through, some came out at different angles, but some, much to the surprise of Rutherford, actually came almost straight back. It was an amazing experiment, took a lot of time. And in the end result, with his scattering experiment, we have an equation, which you'll need to know for the quiz on this chapter, that relates the radius of the nucleus to the atomic mass number. So R is equal to 1.2 times 10 to the minus 15 meters, multiplied by the cube root of the atomic mass number. So let's look at an example and calculate the radius of the carbon-14 nucleus. So we know that the atomic mass number for carbon-14 is 14. We're trying to solve for R, and we have our equation. So we write our equation down, and we plug in. The cube root of 14, so 14 raised to the 0.33333 power is 2.41. So 2.41 multiplied by 1.2 times 10 to the minus 15 gives us a number of 2.8922 times 10 to the minus 15 meters. What is interesting about being able to calculate the radius for the nucleus is that we can show, whoa, overshot. I do this all the time. It's so annoying. What we can do is we can show that both the radius and by correlation, the volume and mass increase proportionally with increasing A. And the conclusion is that all nuclei have approximately the same density. So again, we're talking about the nucleus, not the atomic density, but the nuclear density, because, well, it's just fascinating. I'll move on. I need to focus. So nuclear masses are given in terms of unified atomic mass units, where carbon-12 is defined as having a value of exactly 12.000000 U. U is the unit we use for unified atomic mass units. There is an appendix in the online book, Appendix A, that we'll utilize to look up masses. I'll be providing a hard copy for you in class, but you do need to be able to find it in the online book, just in case. So this is a little snippet of Appendix A in the most recent version of our online book. You can see it's got a column for the atomic number, a column for the name, a column for the atomic mass number, a column for the symbol, and the atomic mass in unified atomic mass units. We won't be using the last two columns in this table, just the one with the mass and the name and the atomic number. So you can see helium-3, He3, has an atomic mass of 3.016030 unified atomic mass units. Please do not round off because the table is given with 6 digits to the right of the decimal. I'll expect your answer to have 6 digits to the right of the decimal. You notice it gives us a value for the mass of the neutron, and you will use it. They give you a value for the mass of the hydrogen-1. Hydrogen-1 has no neutrons, and so we're going to use this for the mass of the proton. The nucleus in hydrogen-1 only has a single proton, and this is the number we'll use. We also need to convert masses into MeV, which is a unit of energy. And to do that, we'll multiply our numbers, our unified atomic mass units, by 931.5 MeV to come up with a unit that makes sense for us. And you'll see in the examples how we utilize it. So let's look at the binding energy and the nuclear forces. We know that like charges repel, and so that means that the protons in the nucleus should want to blow the nucleus apart. But we also know that the nucleus stays together. So what's the deal? The deal is that there are forces that hold the nucleus together. And an interesting aspect of this is that if you looked at the mass of the individual protons and neutrons that comprise the nucleus, you would have more mass if you looked at the little parts than you do when we look at the actual value. And since we know mass can't just disappear, what we assume is that the missing mass, the mass defect, is converted into energy, and that energy is what holds the nucleus together. We call it the binding energy. There is an average binding energy per nucleon, which is equal to the total binding energy divided by the total number of nucleons. Remember, nucleons are the protons and neutrons. So let's look at an example. What's the average binding energy per nucleon for carbon-14? So we will need this section of Appendix A, because we'll need to know the mass of a neutron and the mass of a proton. Remember, we get those from the first 2 entries in the table. And then we'll also need the information for carbon-14. And you can see it's right here. The mass of a carbon-14 atomic mass is 14.003241 U. And we'll put this in our little list of knowns. So I'll let you know where I got my numbers from. Let's put them down. So what we know the mass of the carbon-14 that we'll be using is this number, 14.003241, and it comes straight out of the table. We know the mass of the proton is the same as the mass of the hydrogen-1, and so that's 1.007825. And again, the units are U for unified atomic mass units. And the mass of the neutron is 1.008665 U. For formula, we're trying to find the binding energy per nucleon. And so, whoops, something missing. Here we go. So the binding energy per nucleon is the total binding energy divided by the total number of nucleons. So we're going to, and the total number, the binding energy total is going to equal the number of protons times the mass of one proton plus the number of neutrons times the mass of one neutron minus the mass of whatever element we're looking at. And then times 931, excuse me, times 931.5 MeV to convert unified atomic mass units to MeVs. So we've got the mass of carbon-14, the mass of a proton, the mass of the neutron. We need to know how many of those we have. Carbon is element 6 on the periodic chart, so it has 6 protons. Carbon-14, well, 14 minus 6 gives us 8. It has 8 neutrons. And its total number of nucleons would be 14. So we should have all the numbers we need to plug into our formula. So the binding energy per nucleon is the binding energy divided by the total number of nucleons. And the binding energy is the total mass of protons plus the total mass of neutrons minus the mass of the atom divided by the total number of nucleons. So if we put all that in symbols instead of words, the number of protons times the mass of one proton plus the number of neutrons times the mass of one neutron minus the mass of the nucleus times 931.5 divided by the total number of nucleons. So 6 protons times the mass of one proton plus 8 neutrons times the mass of one neutron minus the mass of the carbon-14. And that has to all be done and then multiplied by 931.5. And then it's divided by 14 because it's carbon-14. So we have 14.11627 minus 14.003241 times 931.5 divided by 14. And we have 7.520465. And the units would be MeV per nucleon. Another way to remember the formula is parts minus whole. So the protons and the neutrons are the parts and the whole is what we look up for the designated atom in the table. If we looked at a graph of average binding energy per nucleon versus the atomic mass number, it would look like this. There's some little sharp peaks, there's a relatively flat area, and then it trails down. We'll refer back to this, but this chart helps explain some things like nuclear fission and fusion and why there's some instability at either end of our atomic spectrum. The nuclei in the middle are held more strongly than those at either end, so the ones in the middle are stable. We have 4 basic forces. We have, well, 4 basic forces. We have the gravitational force, the electrical force, the strong nuclear force, and the weak nuclear force. So the strong nuclear force is the force that holds the nucleus together. It's a short range force. The weak nuclear force is the smallest force, and you see it in certain types of nuclear decay. We'll talk about that in the subsequent videos. And you're already familiar with gravitational and electrical forces. So a nucleus is stable when it's got the right balance of protons and neutrons. For a really light nuclei, that's almost always a 1-to-1 balance. For heavier nuclei, it takes a lot more neutrons to maintain that stability. If we look at the N versus V curve on the following chart, so we have number of neutrons on the y-axis and number of protons on the horizontal axis, and N equal to Z, so a 1-to-1 ratio is right here. You'll notice in the light nuclei, they're stable. Stable are it's the pink region, and all these little red dots are the unstable ones. So in the pink region for light nuclei, so roughly with less than 20 protons, it's a 1-to-1 balance that gives us stability. But as you get heavier and heavier, you'll notice you need more and more neutrons to maintain that balance. And when we get into the upper reaches, there are no stable um, nuclei. I'll get it out. And this is just a different version. What I like about it is it shows you what kinds of decay are required for some of those. So again, the region of the valley of stability, or the region of stability in this graph, are the little blue dots. You can see that the alpha emitters are this sort of pumpkin colored, and this more golden color are the beta plus emitters, and the green are the beta minus emitters. And again, here's that N equals Z line. So let's talk a little about radioactivity. We'll look at some of the history of it. So back in 1895, which is certainly a long time ago, but not that long ago, William Röntgen discovered X-rays. This is actually an X-ray of his wife's hand. It's the first X-ray. They didn't know at the time that too many X-rays could be dangerous. And so it was quite common to X-ray someone's hands just to be able to see the bones. In 1896, Henri Becquerel discovered that radioactivity is an inherent property of uranium. Becquerel was looking at pitchblende, and he was noticing that certain materials glowed when exposed to sunlight. So he would expose them to sunlight, and then he would bring them in, and then he would take a photograph of them, and then he would analyze the photograph. And he had one of his glass plates that was being exposed to a rock that hadn't been exposed to sunlight and wasn't glowing. And lo and behold, when he processed his photographic plate, he discovered that it had been exposed just like the ones that had visible light coming from them. And that led Becquerel to the discovery that there were some things that released energy, just like light is a form of energy, but you couldn't see it. And of course, and that it was an inherent property of the material. It didn't require activation by sunlight. In 1898, Marie and Pierre Curie discovered the elements polonium and radium. They are both radioactive. This is a photograph of the Curies, and I guess what I like about it is that they look young. Pierre died an untimely death. They didn't have traffic lights and crosswalks like we have now, and he was run over by a milk truck crossing the street. Marie Curie, who was just as good a scientist as her husband, she and Pierre shared a Nobel Prize. And then after his death, she won a second Nobel Prize for her work. They had two daughters. One daughter continued her father's research along with her mother. In 1899, radiation therapy was used to remove a wart. The only reason I mention this is I want you to realize we had useful reasons for studying radioactivity, even from the very early days. Ernest Rutherford discovered alpha and beta radiation. He wasn't sure what it was, so he gave them letters of the Greek alphabet, thinking they'd figure it out. And even to this day, we have stuck with alpha and beta. So we need to be careful what we name things. It might stick. In 1902, photographic monitoring for health purposes was first used. And we use this even to this day. If you've worked in a hospital, around the X-rays or nuclear medicine, or you worked in some sort of a lab, you might have seen people that have on film badges. They have a little piece of photographic film inside it, and it's sent off for processing to determine a cumulative exposure to radiation. We'll talk about that a little later too. In 1903, Ernest Rutherford, here he is again, discovered gamma rays. We'll talk about alpha, beta, and gamma in quite a bit of detail in a different video. So radioactivity is the spontaneous changes in an unstable nucleus. It gives off energy and particles in an effort to become stable. Radiation is the form of energy that the unstable nucleus gives off. And what's neat about this is that the radiation that's given off is not impacted by changes in temperature or chemical state or chemical combinations. You can stick it in the freezer and that will not speed it up or slow it down, its decay rate. You can drop it in boiling water and that's not going to change things. You can take and make it an oxide and that won't alter its rate of decay. Transmutation is the changing of one element into another. So when a radioactive element is changed, it's undergone transmutation. And in fact, when it changes, the byproduct that's produced is referred to as the daughter. It's referred to as the daughter. So in a decay scheme, you're going to have a parent, it'll emit radiation, it'll form a daughter, and there'll be energy associated with all of this. The energy is often called the disintegration energy or the Q value, and we'll actually look at these for specific decays. One of the things we want to remember is that in all transmutations, in all changes, nucleons are conserved and charge is conserved. And we'll look at this in specific detail. So we're going to stop our share and stop our